Alrighty.
Sorry, I'm trying to listen.
Yeah, that works.
I want to be involved.
That's good. All right, we're going to go ahead and start. I'm going to start off the meeting, and then I'm going to pass it over to Scott. I need to take attendance. Would you be willing to use the sheet of paper? Just write names and dates. Okay, so today you'll just sign in. In the future, I'll be taking attendance manually, but to save time in our first day, we'll just have a sign-in sheet. So make sure you sign in if you want credit, and I'll gather it in the back. Sorry. Tables. All right. Hello, everybody. I'm glad to see you. You're here for linear algebra. It's a 300 level math class. I've seen several of you in other classes that I've taught, and some of you are new faces to me, so it's good to meet you. My name is Dr. Jane Ann Harder. I am a professor here of mathematics. I've been here since 2012 when I came to ORU. And this semester is going to be a neat opportunity for you, and because you're going to have a guest lecturer this semester. We're going to have Scott Alons, who you have probably seen around. He is a senior, and he's getting ready to graduate with two majors, with a math major and also a biblical literature major. And he has interned before, because one of his things he loves to do is to teach mathematics. And so he's asked, and we've agreed that he will be doing an internship of teaching this semester. So he is going to be doing most of the lecturing in this class, or the running of this class. I am your professor, however, and I am the one who's assigning your final grade in the course. So I'm here kind of observing and available to help you should you need anything. Feel free to come see me. I do have office hours. And I would enjoy getting to know you and having a relationship with you. But I just wanted you to introduce you to Scott. He's going to start in just a moment. We are going to reserve this seat this semester for our recordings, because we're doing two types of recordings, one for his private collection and one for ORU, the Zoom. So students can join us by Zoom if they're sick, or we have some students that are not able to get here because they're having transportation issues getting here on time. So I'm going to start with a prayer for us, and then I'm going to pass it over to Scott. So Lord, thank you so much for this day, for this new semester, for this new year. Thank you for all that you're going to do and grow us this semester. I pray for your presence in this room at all times, that we would sense you with us, that we would enjoy learning new things, expanding our ideas, and worshiping you in the process. And I lift up Scott to you today as he starts the new semester off, that you would anoint him to be the best teacher he can be. And just I pray for a good time together, Lord. Thank you, Lord. In Jesus' name, amen.
Hi, everybody. It's good. It's so good to be back. There's a prayer, and I'm taking a prayer class this semester, and there's one that I want to start with for this semester. It's very appropriate. It's in Luke 18, and you can find it in the parable of the Pharisee and the tax collector. And the prayer is very, very simple. It's simply this: God, have mercy on me, a sinner. And as we go through school, we're all going to make a lot of mistakes. We're going to do things that we regret doing. We're not going to study as hard as we want to all the time, and you're going to probably fail certain things that you wish you wouldn't have failed. So never forget that your God wants to forgive you, that your God is always with you, and that your God is going to define who you are. Have mercy on me, a sinner. And this is the prayer for the semester, and I hope that's your prayer in your personal life outside of this class as well. I promise I'm not a math bum. Most of you already know who I am, but I figure I should probably state some of the things that I've done before. I have had the opportunity to teach Calculus 1, 2, 3, 4, linear matrix algebra, again, calculus, or I already said that one, abstract algebra, algebraic topology 1 and 2, differential equations, some geometry, I've written 2 textbooks aimed at high school students and bringing college-level mathematics to high school. I scored 3 times on the Putnam exam from freshman to junior year, which I believe, as far as records go back, that is the ORU's longest standing record. For my senior thesis, I developed a new branch of mathematics so that I could solve an unproven theorem that is used in music harmony. But above all of these things, I find that my favorite thing is to serve you guys in office hours, in random emails, and questions when you guys come and see me in the Mose line and ask me about Pearson. That's the why I do this. That's why I'm here. It's because I love you guys. Okay? So if you haven't been in one of my classes before, please come up here so I can shake your hand, get to know your name, so I can learn that. I know I recognize most of you, but I really do. I mean that I want to know who you are, and I want to serve you. This class, a few rules. You're going to handwrite all of your notes because it's math. If I write it, you should too. I'm going to say this once for the entire class, and this is the one time I'm going to say it. So if it's on this board, you should probably have written it in your notes. Please read the book. You won't have an excuse for a paywall or follet because this has been successfully pirated on the D2L shell. So the entire 5th edition is available to you. Read the sections. I actually don't care if you read it before or after a lecture, but definitely by the time you submit the week homework, do so. And then do the Pearson, please. I've done this for 4 years now, and so I have actually lost all empathy for people who have a struggling grade because they didn't do 30% of the total homework. Okay, so if you're gonna do less than half of the homework in the class and then you have a C, that is unfortunately no longer my problem. So just do it. It's not complicated. The course calendar is spelled out for the kindergarten level, so you will be able to figure out when everything is due, etc. Does that make sense? I mean, cool. So what are we doing? We are reading, and you're going to do your. Thank you. Okay. Another thing. There's a lot of content in these lectures, and my goal is to never leave anybody behind. So I will, if need be, slow down a lecture so that people can understand at least what we've talked about. That being said, sometimes that means I won't cover everything here. So what I will do is if I don't get through everything I want to, I will then go and later personally record the lecture for the rest of all the remaining content and then add that to the playlist. So then go on and actually watch whatever remaining lecture material there is, especially if you haven't read the text. Does that make sense?
Yeah.
Okay. We're starting off with Chapter 1, Systems of Linear Equations. We should probably define what a linear equation is. I know all of you know what a linear equation is, but let's define it. A linear equation is the variables x1 through xn. This notation is simply denoting that there are n variables. Is an equation that can be written in the form a1, x1, and then so on and so forth through an, xn. And that's going to equal some constant b, where b and the coefficients is an important math word, so we're defining this as well. These are those real numbers a1 through an are real or complex. And thankfully in this class, it's not 400 level, so we will not be doing complex linear equations, but you technically could. For example, if I had 4x1 minus 5x2 plus 2 is equal to x1, tell me, is this a linear equation? Yes, because it is in this form, it can be rewritten in this form. Is this a linear equation? x2 is equal to 2 times the square root of x1 minus 6. What about this one? No, because I have now imposed a square root over the x. Okay, so linear equations are going to be basically, think the easiest possible version algebraically. It's only going to be the variable by itself with a constant. So let's define system of linear equations. This is actually kind of nice. I like this. Okay. A system of linear equations this is what we're defining. Sometimes we just call this a linear system. Is a collection of one or more linear equations. Involving the same variables. Involving the same variables. A solution of the system is a list. And we can call this list by S1 through Sn, depending on how many variables we have, of numbers that makes each equation true. When the values S1 through Sn are then substituted back, so are substituted for your variables x1 through xn. I should say respectively because that's not given. The set of all possible solutions, is called the solution set. So pretty straightforward. Called the solution set of the linear system. And then two linear systems are called equivalent if they have the same solution set. So they could look different, but if fundamentally they have the same exact solutions, then we are going to classify those as definitionally the same. I know a lot of writing, but that's how math typically works. You start off with the definitions, and then you actually do stuff with that. And again, I am aware that if you're in a 300 level college class, you have to have done a system of equations at some point. You probably did one on the SAT you took before you came to ORU. And what we're going to do is we're going to amp up the size and scale of what kinds of systems we can solve by, technically infinite fold. But we do need to recall an important visual intuition. So I'm going to recall from your high school algebra experience, typically speaking, when we have systems of linear equations, I'm only going to visualize two because otherwise it doesn't really make that much sense. But if I have two lines, these are the types of solutions I can have. I can have one solution. In other words, if I have two lines, if I plot those two lines, there's going to be some sort of an intersection point. This is x1, this is x2. And I'm certain that you are familiar, at least with the fact that you could have parallel lines. And if your lines are parallel to each other, how many solutions are we going to have with parallel lines? 0. Okay, so we have 1, we have 0, and then do you know what the third combination is? Infinite, right? So what does infinite mean? It's the same exact line. So I'm making this fuzzy thing so that the lines are sitting on top of each other. Same slope, same exact point, depending on what numbers you're given, but that solution has an infinite number of solutions. So this works in R2. This will work for basically all systems of equations. So visually, be thinking about this. You would be stunned at how many concepts are reliant on just that alone. Actually, you know what? This is important enough that I'm going to designate it with a thing, okay? Now, we're going to come up with some different terminology in linear algebra to describe what we mean by there being a solution or not. So it's important to just have these words memorized so that when you read your text, you don't get confused over terminology. A system of linear equations is said to be, the word we're going to use is consistent if we have any solution. So that could be the 1 or the infinite. So if it has any solutions, doesn't matter how many, just having a solution in itself, we're going to be consistent. And then if we're not, what do you think the opposite is? Inconsistent otherwise. Does that make sense? I think I forgot to say this. I need to say this at the beginning of every class. I appreciate being interrupted, and I appreciate hearing your voices in the middle of a lecture, okay? So vocalize, please. Ask questions, please. Interrupt me, please. Make sense? Okay. So for an example, here is x1 minus 2x2 plus x3 equals 0 as the first equation. I'm going to tell you ahead of time, I've designed this example to show you how you can visualize these equations in your notes when you're solving problems. I'm aligning the variables underneath each other for a very important reason. So 2x2 minus 8x3 equals 8, and then 5x1 minus 5x3. So again, I'm deliberately stylizing the way I've written this to make it organized. And so why am I doing that? Well, I'm going to use this to define something called a coefficient matrix. We're going to see probably a million of these. Well, that's really bad handwriting. A coefficient matrix. Do you remember the definition of coefficient from earlier? That's basically whatever number is the constant that's multiplied against your variable. So it should make sense that a coefficient matrix would simply be a matrix that contains exactly that, the coefficients of each equation. So here, what's the coefficient on this one?
1.
Then, 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 what about this?
0.
Don't forget that. Then,
2.
and then of course 5, 0 minus 5, 10. And I'm going to do something that is just a stylistic thing. Okay, so it's not like an actual math symbol, but I like to dot this off. Just because in my mind that lets me know this is the stuff that was on the other side of the equals, and these are the actual coefficients of my variable. Again, you don't actually, this is mathematically not really anything. It's just a visualization to keep your notes clean, to keep your problem solving clean, and easier to understand. Okay. So, I made a mistake already. The coefficient matrix does not have that side yet. It's strictly the coefficients. The next definition is the augmented matrix, which is going to have that dotted thing. So the augmented matrix. Apologies if you wrote that in your notes in pen. So 1 minus 2, 1, and 0. No, it's funny. When I was taking all the math classes, I massacred trees beyond belief by the number of notebooks that I filled with mistakes. I don't think people appreciate how much of good mathematics is making the mistakes and then correcting them. So if you feel like you're slow, well, I have learning disabilities, so it's all good. Any questions about the difference between a coefficient matrix and an augmented matrix?
What was that? What was the side on the right? What do the numbers represent there again?
Oh, like with the dotted off ones?
Yeah.
These numbers represent whatever the constants are here that we're equal to, yes. And that actually, being set aside, is going to become very, very important on Friday. Okay, we all good with this? The key here is to always be able to relate a coefficient matrix and be able to go in between these, translate between these. If I see a system, in my brain I'm seeing this matrix. If someone gives me this matrix, I'm seeing the system. Go between those in your head and this will go very, very easy for you in the class. Where was this rack in Calc 3? That's amazing. Okay, definition. This is a 300 level class, so I figure it's about time you learn some grown-up math symbols. Upside down capital A is the English words for all. For all. Okay, so for all, M and the commas, if you see a comma, put the word and in. You will almost always read it correctly. So for all, M and N. This guy means in. We've probably seen this one before. And then the capital double struck Z is for integers. And if I subscript it with a plus, that just means I want positive, okay? So for all positive integers, M and N. And M by N matrix is a rectangular array. Rectangular array of numbers with m rows and n columns. Why am I defining this? It's just because it's really convenient to know what I mean when I say 5 by 4 matrix, for example, versus a 4 by 5 matrix. So this one right here would be how many rows, how many columns. So this is a rows by columns matrix. How many rows? 3. Rows by how many columns? 4. Bingo. So that means we can't necessarily flip those numbers around and be okay with that. The order matters. And then the order matters very visually because the rows are going to go down, columns come across.
In that last definition, next to the Z, is that a subscript plus or is that plus?
It's a subscripted plus. It's a very good question. Okay. So if I subscript a plus next to a common number set, that's saying take only the positive elements of that. Yeah, so I'm taking only the integers, and then I'm saying integers, make that only the positive ones. And that's just a really fast way to notate it. Good question. Okay.
What's MXN matrix?
Oh, and M by N.
Oh, M by N.
Yeah, so whenever we put the times between this with matrix specifically, we're then describing an actual matrix. So this is distinguishing how many rows you put there, how many columns you got there. Cool. Anything else? Cool. There are certain operations we can do in mathematics, and depending on what objects you're dealing with, we can do different types of things. So these are going to be considered our elementary row operations. And this is going to be how we interact with matrices. The first one is called replacement. Everybody say replacement. Replacement. That was really weak. Everybody say replacement.
Replacement.
Number 2 is interchange. Say interchange.
Interchange.
And then the third is scaling. Say scaling.
Scaling.
Okay, so replacement, shocker, is going to be replacing rows. Interchanging is going to be interchanging rows. And scaling is going to be scaling rows. So we will actually work through a problem so you can see exactly what this means, but they actually describe themselves pretty well, so I don't really need to teach that. There's another definition we need before we move on to the actual algorithm. And for the computer science people, I don't know if the way that the textbook is treating the word array here for rectangular array is that similar to what you study or if it's a different perspective. Either way, I apologize if it's different, but otherwise, just learn the math way for this class. Okay. Definition. Two matrices are called row equivalent. So this is very important. Row equivalent. If there is a sequence of what? Well, maybe what we just defined here. Elementary row operations. That transforms one matrix into the other. Okay, what does that mean? Well, if I start with some sort of a matrix, and then I decide to replace one of the rows, then I decide to interchange some of the rows, scale maybe a few of them, maybe do another replacement. Ultimately, if I can trace back those exact steps in that exact kind of domino chain of row operations, the new matrix that I still end up spitting out, we're going to consider them to be row equivalent. So, I designed a little graphic here to help us out. So, linear system. First question we're going to ask is if it's consistent. Somebody, what did consistent, essentially, what concept is this relabeling consistent? Yeah. I mean, does it actually have some intersection? Is there some intersection there? So, there's two answers to that. We're either going to say yes, or we're going to say no. Now, if we say yes to the consistent question, remember there are three options here. So now we have to question, is this solution actually unique? Or is it just one of an infinite slew of described solutions? And so if the answer to that is yes, if we do have a unique solution, well then, logically, how many solutions?
One.
Yeah, there can only be one. What were the three outcomes again? You can have how many solutions? Infinity. Okay, so if we know we have a solution and we know that solution is unique, what does that make? One solution. What if we have solutions but we know that it's not unique? What does that tell us about the number? Infinite. And then of course, definitionally, if the answer is no to being consistent, we know that our system, what word would we use to describe that?
Inconsistent.
Inconsistent. Which implies that's the same statement as there being zero solutions. Note on notation for you note takers, because you have obviously been handwriting every single thing that's been written on the board. Whenever you see a double direction arrow, this is if and only if. Another way to think about it is whatever statement is on the left and whatever statement is on the right, they are logically equivalent. Meaning that if I say this, I could have just said that. And likewise, instead of saying this, I could have just said that. And in the force of logic and the force of a proof, they are exactly the same. Does that make sense?
Yeah.
Okay. So now let's actually get to the algorithm here. Do you need anything on this whiteboard before it says goodbye? Okay. Does anyone need on this whiteboard before it says goodbye?
What does the Z mean again?
Capital bold stroke Z is going to be the set of integers. So your integers are going to be your 1, basically no fractions. 0, 1, 2, 3, etc. And then you turn around and go down the negative direction. Okay. We good to clear off this whiteboard now? Okay. We're kind of moving into 1.2 topic area. Let me double check the time just so I don't waste your time. Okay. So we need a motivation for this algorithm. So I'm going to put here, motivation. Motivation is really important, not in the stereotypical sense, but in mathematics. If I just show you concepts, you're going to be like, fantastic, that's a concept. And instead of doing that, I'm going to tell you, I'm going to set up a situation, and then that's going to motivate why we introduce something. If you know why you're doing something, you're going to remember it way better than me telling it to you. We're going to compare the augmented matrices. We're going to look at two of them. Okay, so the first one is going to come from this linear system. x1 minus 2x2 plus 3x3 equals 4. 0x1 plus 5x2 minus 7x3 is equal to 1. And then 10x1 minus x2 minus x3 is equal to negative 4. So, if I wanted to describe this system using an augmented matrix, somebody, what's the top row?
1, negative 2, 3, and 4.
What's the second row?
0, 5, negative 7, 1.
And then the last row?
10, negative 1, negative 1, negative 4.
Okay, again, this isn't like a math thing per se, but I'm dyslexic, so it helps. There is that matrix. We're going to look at another system. Suppose I had x1 plus 0x2 plus 0x3 is equal to negative 1. 0x1 plus x2 plus 0x3 is equal to 0. And x3 is equal to 4. Okay, this is still a system of linear equations because the coefficients are real numbers and we have the same variables. But you'll notice something very visually kind of satisfying when we make this augmented matrix. Okay, so now what's the top row?
1, 0, 0, 1, negative 1.
Second row?
0, 0, 0.
Third row?
0,
0,
0,
0, 1.
And then again, I'll set up what the equal sign is. Okay, so which one is easier to read? And which one gives you more actually useful information about the variables? So wouldn't it be remarkably convenient if we were able to have an algorithm that could transform any type of matrix that originally looks like this into something that just spells out to you what the solutions are? Okay? And this is what we're going to spend a lot of time doing in this class. A mess, which comes from a mess, made into a not mess that you can interpret and get solutions. Okay? Does this make sense? Do you like looking at this or this one better? Yeah. What we're going to do is, this is not a formal definition, but now that we've motivated this is an augmented matrix. When we get it in this very specific form, the form that's basically going to tell you exactly what each variable is, we have a special name for that. We're going to call these reduced echelon form. Another thing that we sometimes call it is a reduced row echelon form because we use row operations. So both of those terminology, it's the same exact thing. So I could, when I was looking at the textbook and how they were explaining the algorithm, I almost couldn't understand it because it was kind of horrendous. So what I'm going to do instead is I'm going to just go through one. And by demonstrating what kind of ways you can break down these matrices, it'll be much easier to practice on your own, and then you'll actually need to do one for Friday. Okay, so let's start off with an ugly one. 0, 3 minus 6, 6, 4 minus 5, 3 minus 7, 8 minus 5, 8, 9, 3 minus 9, 12 minus 9, 6, 15. Okay. I don't know, you have it written down, or you should have it written down. We had 3 options to do row operations. And now when we look at the way that this is structured, we obviously want there to be that 1 at the very top corner. So there being a 0 is kind of a problem. So I'm going to interchange 2 rows. This symbol that I'm using between them, this is the symbol notation to describe that 2 matrices, although they have different numbers, are row equivalents. I've performed some sort of row operation, but it comes from something. They're related. And then above, you don't have to do this, but I would keep track of what your steps are. I'm going to say I'm interchanging, let's say row 1 with row, let's do row 2. So I'm going to interchange these. So I know that these are row equivalent, and I'm leaving myself a personal annotation so that I don't get myself confused. Okay, so if I do that, I just need to rewrite this with the second row where the first row is. So now the first row is 3 minus 7, 8, minus 5, 8, 9. And then the second row becomes what the first one was, so 0, 3 minus 6, 6, 4, minus 5. And then the bottom row stays the same. 3 minus 9, yes?
Is that a math symbol or a U symbol with the R1 dash thing?
Oh, this is a me symbol,
Okay.
so that I remember that I'm interchanging those 2 rows.
Okay, cool.
It's a good question. The math symbol is this one.
Cool, that's good.
Yeah. 3 minus 9,
It's standard though,
minus
notation.
9, 6, 15. In general, with notation-related questions, it depends on what branch of math you're doing. Yes.
So are they still the same or no?
Well, are they equal? Are the matrices themselves equal? No, because they have different numbers and different values. However, we would say that they are row equivalent because they are related by at least some sort of predictable chain or documentable chain of these operations. Does that make sense?
Yeah.
Okay. So that's why we use the word equivalence instead of equals. So we're going to do another one. And now, we need this to go away. This needs to be a 0. So every single time I'm going to start on the left like a typewriter, and then knock the zeros all the way down, whatever the first one is. Okay? So what's a really convenient way to relate 3 and 3 and get 0? Yeah, just subtract them from each other. So what I'm hearing is I could just take row 1, the value of row 1, subtract whatever the values are in row 3, and then replace row 3. So I can take 3, I can subtract 3, and then just replace out that entire bottom row with whatever this new difference is, and that's going to give me my convenient 0. Does that make sense? Okay. So what's nice about this is that we're only changing 1 row. So when you're rewriting this in your notes, it helps to know you can just rest in peace. Write the ones that are unaffected first before doing the affected one. So I got 3 minus 7, 8, minus 5, 8, 9 that are unaffected. And I have 0, 3 minus 6, 6, 4 minus 5 that are unaffected. Now I get to the affected one. So row 1 minus row 3. What's 3 minus 3? 0. So that becomes the new entry. Minus 7, subtract 9. So, or subtract negative 9.
2?
Positive 2.
Is that meant to be row 1 minus row 2 equals row 3? Or is that
Row 1 minus row 3 equals the new row 3.
Yeah, I'm taking row 1, I'm subtracting whatever corresponding value is in row 3, and then that's getting replaced in. Good question. So then 8 minus 12 is minus 4. Minus 5 minus negative 9, positive 4. 8 minus 6 is 2, and 9 minus 15 is minus 6. Okay, this is the hardest operation to do. So if you understand that, you're golden. Okay? Thumbs up if you like that. Makes sense. You can do it on your own. Cool. All right. So we succeeded. We got a 0 here. And now we need to move on to the next structure. So notice that the stair-stepping structure goes on. We need to go to the next one, diagonally under, and then zero everything out again. So this becomes the new point of interest right here. I want to clear out everything underneath the next, we call this pivot more formally later. Okay, let me think. All of these numbers on the bottom you might recognize are even, which means we can probably simplify that. So I'm going to do the operation of scaling. I'm going to take half the value of these numbers in row 3, and then use those easier values and replace that bottom row. Does this make sense? Is what I'm trying to communicate with that notation make sense? Okay. So then again, which row are we really only affecting? Okay, so when you're writing the next step, don't sweat it. Just write the top two again. So 3 minus 7, 8 minus 5, 8, 9.
Are
0.
these augmented matrices?
Yes, they are. Notice that I did not place a little thing there. That's just because if I did that for every single one, my eyes would start tripping out on the whiteboard. But you can on your paper if you want to, if it helps. Okay, so we're on the last row. 0 divided by 2 is 0. 2 divided by 2 is
1,
minus 4 goes to,
negative 2,
then,
2,
then,
1,
then.
minus 3.
Beautiful, you guys can do linear algebra. Alright, so now this just got a lot easier to do, because if we were trying to eliminate that 2 and relate it to a 3, that's kind of horrendous, but now it's just this 3 and a 1. Okay, so we think, what combination can I do to this to replace out this bottom row so that strategically the one underneath this guy turns into 0? And I know for myself that 3 minus 3 is 0. Is this 1 a 3?
No.
No. Could I multiply this 1 by a convenient scalar to make it 3? Yeah. So I could take my second row. Well, you could actually do this either way. I'm going to stick with my notes because I'm a arithmetic liability. So I can gonna triple the value of what this third row is. So that's gonna turn that 1 into a 3. And then I can subtract the value in R2, so it's 3 minus 3. And now, take a look. Which row is being affected? Oh wait, I forgot to say what we're replacing. What are we replacing here? R3, right. So if we're dealing with R3, should we be worried about the top 2 rows? No, so let's transcribe those. 3 minus 7, 8. Minus 5, 8, 9. 0, 3, minus 6. 6, 4, minus 5. Don't worry, I can already hear the plea of, Scott, my notebook does not want to tolerate this for an entire week. Well, buy more paper. Okay, so we're going to triple the value of the third row because that's what this says. Then just subtract the value. So what's 0 minus 0? Okay, triple the 1 gives you, subtract 3. Shocker. And then triple this. Okay, so it's the same value subtracted by itself. Triple that. Okay, so minus 1 times 3 is?
3.
If I take 4 away from 3, I have to do what? And then if I triple that,
Negative 9.
and if I subtract a negative 5, so I add 5 to negative 9. Voila. Well, that cleaned up very nicely. Okay. So, you might be thinking, if I'm stepping down this pattern, we might be expecting the next one to be the pivot. But you'll notice that this is not very well behaved. I started here, and that was nice. Then I cleared the zeros under this one. But if I go down diagonally, that doesn't make any sense because I hit the bottom row. So what I do is I travel across until I find the next pivot, which becomes this minus 1. Does that make sense? Okay. Thumbs up if you could make that identification on a problem later on your own. Okay. In that case, I think we'll talk about it more in the lecture also on Friday, so that's good. in this case, we want a positive 1 right here. We are now on the back end of our process. You'll notice that we have a nice staircasing thing going on with all the zeros underneath, but now we actually want it to look like this. So I'm going to put, what can I multiply by -1 to make it just regular 1? So I can take negative version of R3 and then just replace R3 with that. Which row is being affected? Okay, so should I worry about the top two? No. So we get 3 minus 7, 8, minus 5, 8, 9, 0, 3 minus 6, 6, 4 minus 5, and then 0, 0, 0, 0, 1, 4. Okay. Yes.
To make sure, if I just wanted to literally just say, for R3, I can make it to R1, R2, I could just keep mixing them up and it'll still be row equivalent, right? If I just keep mixing.
This is a really, really good question. When I took this class, I thought that I could be manipulating multiple rows at a time to save time, because trust me, I know that this is boring, okay? But the problem is, if you're doing if you're trying to change out, say, the first 2 rows, but then simultaneously trying to switch out the second row with then a third row, you're actually no longer doing that operation to that second row because you've interchanged it. So be very, very careful with when you interchange and when you replace. Because if you're trying to do a replacement and an interchange, or a replacement and a replacement, on 2 of the same rows that's being changed before you've had a chance to accommodate for what that change is supposed to be, suddenly all your numbers are going to be messed up, and then you'll waste 15 minutes doing arithmetic, okay? So just save yourself the time, do these one at a time. That being said, the back direction does allow for you to do multiple steps at a time. So actually, conveniently, we have a term for this one. By the time we get to this stage, when we've cleared everything, we can actually call this an echelon form. Now, notice I have not called this reduced echelon form because we haven't cleared out all of the rest of the zeros and left only ones. But we've left it in this kind of step-like triangular pattern with zeros underneath everything else. So we call this echelon form. And the reason why it's nice to have a name for this is because all the work that you will do from the very beginning stage to your echelon form, we call that I think it's just called forward phase, yeah. We call this entire phase the forward phase. The forward phase is way horrible. It's just not fun to do, and it will be less fun to do than the backward phase, which is much easier to do. Does that make sense? Mm-hmm. Okay. So now what I'll do to save whiteboard space is I'm going to, everyone got this on their paper? Okay. I'm going to clear this, and then we'll pick up from our echelon form to the end. You may be able to infer, if we called what we just did the forward phase, what we're about to do in the reverse direction is going to be called what, you think? It's like you guys read the book before coming to lecture today. Crazy. Okay, so I'll put the last step that we were just on. We were on 3 minus 7, 8 minus 5, 8, 9. Also, what time is it? I don't want to run late on you guys.
2:04.
Oh, okay. So remember that whole thing about I will record whatever I wasn't able to talk about? That's happening on day 1, apparently.
Yeah.
Okay. Life happens. All right. What we're going to do now is we're going to do 2 things at a time. So I'm going to start introducing this because that lets us know that we made it to our 1. And the reason why we want this to be a 1 is because a 1, as we found earlier, was really convenient to cancel stuff with zeros, to get to 0. So I can actually do 2 manipulations because the row 3 is now unaffected for the rest of this. So if I want to replace out the top, I take my row 1 and I think, all right, I have an 8 stuck there. I need to blow that up to a 0. So I need to subtract how many times my 1? Yeah. So 8 R3. And that's going to replace which row? R1, good. What do you think we're going to do parallel to the 4? We're going to take R2. We're going to subtract what?
4.
And then we're replacing that. R2. Okay. So now we can do multiple steps here. 3 minus 0. 3. Minus 7 minus 0. 8 minus 0. Minus 5 minus 0. 8 minus 1 is convenient, or sorry, 8 minus 8 is 0 by design, coincidentally. And then 9 minus how much? So then that gives us, yeah. Okay, now when we do to the second row, just make sure you flip rules. It's an easy mistake to make. So 0 minus 0, 3 minus 0, minus 6 minus 0, 6 minus 0, 4 minus 4 by design, and then our minus 5 minus 4 times this 4, so 16. So we have negative 21. Did I just check my notes for that arithmetic? Yes, I did. Okay, and then 0, 0, 0, 0, 1, 4. Okay? Now, there's no pivot there, so we leave this alone. No pivot here. That being said, to make our arithmetic easier, gee, all of these numbers are divisible by 3. Okay, so let's make it easy. And divide which row? So 1/3 of R2, and I'm replacing that to R2 again. So I have 3 minus 7. The top row is unaffected, so I'm not worrying about it. 0, 1, minus 2, 2, 0, minus 7. And then 0, 0, 0, 0, 1, 4. Okay, so there's really only one more 0 to make here. If I take R1, what do I need to get rid of here? So I'm trying to get rid of this minus 7 and turn it to a 0 because it's over one of my 1s. So I take R1 and well, you could do this a lot of different ways actually. I can add it to 7 times R2. Because what's minus 7 plus 7? And then replace R1. So then 3 plus 0 minus 7 plus 7 by design. 8 plus negative 14, so 8 minus 14. Minus 5 plus 14. And then zeros. And then minus 23 and 49, negative 49. That's going to be negative 72. And then this row is unaffected. 0, 0, 0, 0, 1, 4. Okay, last thing to do. What are all these conveniently divisible by? 3. So I'll take 1/3 of that row and replace it. Okay, we'll make it. So then, lastly, 1, 0, minus 2, 3, 0, and then 24, right? Minus 24. 0, 1, minus 2, 2, 0, minus 7, 0, 0, 0, 0, 1, 4. Now this is nice because, and we call this our reduced row echelon form. What time is it?
209.
209. Okay, perfect. So this is going to be our backward phase. And now you know how to run this. What I will cover in a post, I will record the recording of the rest of this. Talk about how to interpret this so that we know why we even went through that entire conundrum in the first place. And then a little bit more. Yes?
Is there a reason, should we always do forward phase, then backward phase?
Yes. Because if you don't do the forward phase first, then all those convenient double moves don't work. So you can't do multiple rows at the same time because you haven't cleared your bottom.
Okay.
Yeah. So the goal is to get through the forward phase so that your entire bottom row is locked in, and you can use that to pivot everything else. Yes,
So
actually.
what's like the purpose really of like doing the forward and the backward phase?
What was the?
Like what's really like the purpose of it?
We will get into that in the next lecture. Yes. So right now it's just the mechanics of it, and then we'll talk about why we're doing these mechanics.
Okay.
Cool.
Your attendance is noted in D2L. You might double check before you leave that.
And then these are going to be due on Friday when you come to class. Okay, so I'll give you a chance to practice. So take one, pass one. And then real fast. If I can have everyone's attention real fast. I'm going to put my contact information on D2L. I fully believe in helping you guys with everything that I got. I have a light semester, and so I've budgeted a ton of time. That being said, if you do not reach out to me, I cannot telepathically know that you need some help with something, and so then I cannot help you. So reach out, schedule appointments, email me questions. That way I can actually provide any understanding that might have been missed in a lecture. And then I will upload the YouTube playlist link to the D2L as well. Cool.